Okay, so since we didn't get to do this in class, I wanted to make this quick video annotating your periodic table for the test as well as the formula sheet. So we'll start with the periodic table. First off, just make sure you have the charges on there, right? So 1 plus, 2 plus, 3 plus, so that's your 4. And remember, these are minus, 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 plus, 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 3 minus, 2 minus, 1 minus, of course that one's 0. The funky guys in here, remember zinc is 2 plus, cadmium is 2 plus, and silver is a 1 plus. Anything else in those groups 3 through 12, they will provide you with the Roman numeral or the actual just formula. So really the only thing you need the charges for is when you're writing the net ionics. Another thing that you may want, if you don't have it on the reverse of this, you may want to write some of the most common polyatomic ions. So again, that's nitrate, sulfate, carbonate, phosphate, hydroxide, ammonium. Those are the 5 most, or the 6 most common ones we end up seeing. You may want to have your other list handy, but really that's most likely what you're going to see if you see any of the polyatomic ions. So we've got that stuff on here. We might also want to make sure that you've got, in general, a section of the electron configuration portion written, so that if you're asked to write an electron configuration, you've got that down. So the pattern in general just goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, not that they would ever go this far, but we might as well finish it out. 7s2, 5f14, 6d10, and 7p6. Like that takes you all the way to oganesson there if you needed it. So you've got the full length of the electron configuration written down. I think the periodic table is also a perfectly appropriate place to put information about your periodic trends. So remember francium here, that is your largest atomic radius. Okay. So that's reminding you that everything is going down and to the left for atomic radius. Then we remember here that fluorine is the highest electronegativity. Electroneg, we'll do that. And helium, my bad, is your highest ionization energy. Okay, so that'll help you remember the trends. And then another thing that I want to put on here, which I think is really going to help you with your explanations, is the stuff about Coulombic attraction. So which region of the table has the highest and which region of the table has the lowest? We'll start with the lowest. So over here, next to francium, this is your lowest Coulombic attraction down in this region. And that is because you have an incredibly large distance. All right. You have a large distance between your protons and your electrons when you're all the way down at the bottom of the periodic table, right? So large distance going down this way. And then when you are looking left to right, on the left-hand side, you have a smaller nuclear charge, right? So you have a smaller amount of charge and a larger distance, and that is going to give you a small attraction, which means it's the exact opposite period or space on the periodic table that is going to give us our highest attraction. So on this other side, we are going to say we have your highest Coulombic attraction this way, because at the top of the table, you have a very small distance. And if you have a small distance, then you can have a lot of attraction. And on the right-hand side of the table, you have a higher nuclear charge in comparison to the left. So anything involving attraction, involving electronegativity, ionization energy, size, anything involving that sort of stuff, if you're going to talk about Coulombic attraction, if you're dealing with things in the same group, up and down, you want to talk about distance, right? And if you're talking about things that are in the same period, left to right, you want to talk about the nuclear charge. So pay attention to that. And I think that's the basic stuff you're going to want on your periodic table. So let's go to the formula sheet now. And for the formula sheet. Okay, so a couple of things here. First off, the atomic structure, you know, we're never actually going to use those two equations separately. They always have you use them in their combined form, which is going to be h frequency over wavelength. And then the other way to think of it is that wavelength is h, oops, and I didn't mean to say HV, that's dumb. I meant to say HC, right? HC, all right, and you got it that way. And remember, for your wavelength, they will give you the wavelength in nanometers. So just write, for example, 408 nanometers equals 408 times 10 to the negative 9th meters, and that's how you'll have to enter it. You'll have to put it in that way. That's really the only thing for atomic structure that you may have to use. I don't think that the chances are very good that that's going to be on the test. So next, the equilibrium section. We actually get to mark a bunch of this stuff out because it was all from Unit 8. I'm not doing that, or 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 any of this. So you really just need these two here. But the thing we want to put on here is the information about Q. So don't forget, we did it alphabetically, K and Q. So if K is greater than Q, that means you are going to proceed forward. You are not at equilibrium yet, so you will proceed forward. However, if Q is larger than K, you overshot and you need to proceed backwards. So you can use the word forwards and backwards. You can use the word towards products or towards reactants, or you can use the words move right, move left. So if we want to make some notation over here, right, forward, products. Those all go together. And then it would be left, backwards, and reactants. That all goes together. So other things to put on here. There's nothing on here about Le Chatelier's principle. So as a reminder for Le Chatelier, if you add reactant, it'll shift this way. If you add product, it will shift backwards. And then if you remove reactant, it will shift backwards to replace it. If you remove product, it will shift forward to replace it. Increasing pressure, which is the same as decreasing volume, goes to side with fewer gas moles. And then the inverse of that, right? Decreasing pressure, which is increasing volume, side with more gas moles. All right, for temperature, it's going to be based on whether or not it's endo or exothermic. So let's remember that. All right, exothermic means heat is a product. And once you remember that heat is a product, then it's like adding or removing a reactant or a product. And endothermic means that heat is a reactant. And you guys did well with this, so I think you'll be fine. Then the only other thing that I would put on here is just a general setup for an ice table. If you'll remember, it was like A plus 2B goes back and forth to say like AB squared. All right, let's do that. ICE. And remember that your 2 comes down here to a 2x. Remember that you have to do that. So that's kind of your general setup for how to do an ice table, if you remember. For the kinetics, we can add some stuff here. First off, let's label what each of these equations are. They're in order, but this is 0 order, first order, and this is second order. And remember that this half-life applies to first order only. So if they mention anything about half-life, they are telling you that is a first order reaction, and that means this K here is the exact same as that K there. So I want to do a couple of things for my units, because kinetics units tripped you guys up. So we'll just make a cheat sheet of what the units are for a 0, a first, a second, a third, and a fourth order overall reaction. So if you are a 0 order reaction, you are molarity over time. Pay attention to the time units. They're normally seconds, but it might be minutes. If you are a first order reaction, you are literally 1 over the time. If you are a second order reaction, you are 1 over molarity times time, and then it goes up from there. 1 over molarity squared times time, and the fourth would be 1 over molarity cubed times time. So the molarity is always one smaller exponent than the actual overall order. So those are going to be those. The other thing is the graphs. So remember that a 0 order graph is going to be concentration and time, okay? And it's going to be this, and here K equals the absolute value of the slope. If it is a first order reaction, it is going to be the natural log of the concentration against time. We'll also provide a line like that. And the rate constant would be the absolute value of the slope because it's a negative slope. And if it is a second order reaction, then it is going to be the inverse of the concentration versus the time. And that one will be the positive slope. It's the only one with a positive slope. So K will be equal to the slope. You can always just be careful and say it's the absolute value of the slope. I think the chances of them having you determine rate data from one of those tables is pretty small because it can involve math as well as a lot of time. I think kinetics are more likely to involve reaction mechanisms. So go look back at that. There's no real notes to put here, as well as looking at the graphical interpretation. So pay attention to see if there is a graph. And remember, what you're looking for is if you graph the data in these three different methods, only one of those graphs will give you a straight line. Whichever one gives you a straight line, it's what's on the y-axis that tells you is it 0 first or second order. So that's this side of the formula sheet. And then we look at the back. So on the back side of the formula sheet, everything in the gas, liquid, and solution is totally fair game. So we did cover all of that. I do want to add on here our other iterations of the gas law, ideal gas law. So we have PIM dirt. All right. And again, where that M is my molar mass and the D is the density. So that is one way to look at that, or you could call it what the molar mass is, dirt over your P. So that's a thing to look at. Remember that for volume displacement of a gas, you have to subtract the vapor pressure of water, right? If we're collecting a gas of water, that was that lab technique. And again, the combined gas law equation isn't on here, but we can write it on here if you want. It was P1 times V1 over T1 equals P2 times V2 over T2. Otherwise, let's make notes about deviating, all right, deviations from ideal, right? If you're going to deviate from the ideal gas law, two things. Particles have volume, and that is not spelling of volume, that's fine, and they have attractions. So because they have attractions, that actually decreases the pressure because they're attracting to each other. They are not bouncing against the walls. That's the one that they ask the most about. Let's see here, anything else? Not really. You've got your molarity equaling moles over liters, but remember you can also make that moles over 1,000 milliliters. That should be it for that. Thermodynamics and electrochemistry. This was a combination of Unit 6 and Unit 9. We actually went over almost all of this, and you're going to be mad because I'm going to start crossing stuff out that's no longer on it because it was technically in 9. So these two things are the one thing we didn't get to, but there is nothing about delta G on the test anymore. And there's nothing about delta S. There's nothing about entropy, and there's nothing about Gibbs free energy because those were in Unit 9. So I taught them to you, but they're not on there. Isn't that annoying? All right, so Q equals MCAT. Remember that the Q of the system is the opposite sign of the Q of the surroundings. So that's important to remember, that the delta T is temperature final minus temperature initial. That endothermic means that the surrounding temp decreased. Exothermic means that the surrounding temperature increased. And the reason I say the surrounding temperature specifically is because in calorimetry, you are only measuring the surroundings. That's the water. This is your coffee cup calorimetry. Your M, your mass, pay attention because if they talk about solutions, so if they're talking solutions, then the mass equals the water plus the dissolved solid, which is how we did it, just so you know. The specific heat they will always give to you. They have to. The other thing is in here. So a couple other things. So this was one method for solving for H. This was a second method. If you're using Q equals MCAT, you can get delta H by taking Q and dividing by the amount of moles. That's how you typically finish that problem off. A third method was bond energy. Okay. And bond energy was you get the delta H equals bonds broken minus bonds formed. Okay, and this is where we kind of said, oh, this is backwards because these are your reactants, these are your products, bonds broken minus bonds formed. This is where you're going to have to draw out the structures, count the bonds. However, what I think they will probably do is if they ask you to do this calculation, it's going to be tied into a question where they give you Lewis structures already to save you time, so you don't actually have to draw out the structures to be able to answer the question. So there is that on there. And then the other things to do, don't forget, if they give you a set of equations, all right, then you will flip, multiply, and add them together to get what they are asking for. Okay, so that's the other way that you can kind of do that sort of problem. So these are general notes. If you have any questions over any of this stuff, just send me a message and I can go over that with you.